welcome to Science Camp. My name is Mr. Stoker, and we're here in Meridian, Idaho at Mountain View High School filming this. That's where I teach physics, but I also put on science camps in the summer, and we're recording this so that you can have an opportunity to do a science camp like this at your own house, even though you might not live close to one. So I want to start off by talking about what science is a little bit, and I have a demonstration here to be able to do that. I have here a kind of a crystal light. I guess it's got LEDs in the bottom. Okay, here's a close-up of the crystal so you can see what it looks like. It's just a light, it's not really a crystal. And I'll turn it on so you can kind of see it. We'll hit the lights, and you can kind of see that it's got a bluish purplish color. I'll try to move it and see if you can see there's a bit of different colors there. And it's even better if I take it and spin it by the end of the string here. And you should be able to see that it actually is made up of three colored lights, a red, a blue, and a green. That when they all flash quickly or together, it seems to give you this whitish, slightly purple or blue color. The importance of science is that there's a lot of things in the world around us that aren't actually the way they seem to be. And so we need a way to find evidence to collect data to figure out what's really going on. And that's really what science is all about. Now, this camp isn't just science in general. It really is more physics sort of things. But I named it Science Camp because I think that more people understand that. But really what we're going to be learning is about physics. Physics is a branch of science that a lot of people say is the most basic of all sciences because it involves things like energy, force, motion, electricity, magnetism, waves, sound, and light that are involved in lots of other branches of science. And it's one of the first branches that actually developed throughout history. So a lot of this will be physics, but we call it Science Camp. So I'm going to start off today with a demo. Demo is short for demonstration. This is kind of a classic one, the tablecloth tug. I have here a tablecloth, and I have some place settings here. And I'm going to set these on the table. And the idea then is for me to be able to quickly pull out the tablecloth and get the place settings to stay on there. We'll see if I can do it. All right, are we ready? Little drum roll, please, from the peanut gallery. 1, 2, 3. Slight quiver in the glass, but we got it to go. Now then the question is, well, why does it do that? Well, these objects have mass or they have inertia. So they want to keep doing whatever it was that they were doing, which is staying in place. Now it requires something to get them to move, which is a force, in this case friction. And I'm moving this quick enough that friction doesn't have time really to get it going much. The glass a little bit, but the rest of them fairly well stayed in place. Okay, so I wanted to just explain real quick what your homework assignment is. The assignment is right before Thanksgiving dinner, this next Thanksgiving. I want you to say to everybody, I'm glad you guys are gathered here, but before we're going to have dinner, I have a quick demonstration to show you. And so then grab the tablecloth for the nice Thanksgiving spread and do the tablecloth tug for them. So that's your assignment. Actually, don't tell your parents that I said that, okay? But just do the assignment. If you're going to do this at home, there's a couple of tricks you need to know. One is this isn't really a normal tablecloth. I got like a piece of silk or something that's very smooth. And most tablecloths have like a fold over the edge that's sewn down that's called the hem. And that tends to catch dishes and pull them off. So you want to be careful with that. You want to get one that has a small hem or doesn't have a hem at all, actually. The other thing is I used dishes that were heavy. They had a lot of inertia to them. That makes it easier. You need to pull quickly, as you saw me do, kind of snap it almost and pull downward. If you pull upward, it tends to increase the amount of friction and you'll pull stuff off with you. This dish right here has actually been busted a few times, so we've duct taped it and packing taped it up. But so don't use something that's like antique or something like that. We'll see if somebody else can do it here. We'll have Carson come over and see if he can do this. But since we're worried about it, we'll use the old dish. Okay, come on over, Carson. And we'll see what he can do here. Here we go. 1, 2, 3. Look at that. He's good, huh? Now, if you were here, I'd have you do it live as well, but you're not. So if you can find a dish and some kind of cloth at home and try this, you really get a feel for inertia a little bit better. Just don't use your favorite one, just in case. Okay, for this part of this demonstration, I want you to imagine that you're hanging out this afternoon up in outer space. And while you're hanging out up there floating around, all of a sudden this leprechaun pops out of nowhere. Boop, and he says to you that he has a riddle for you. And the riddle is this. He has 2 identical looking basketballs. One of them's filled with like lead or heavy rocks, and the other one is filled with styrofoam. Right? So you try to squish them and you can't tell which is which. And his riddle is, can you figure out which is filled with lead? Because if you can, you get like a lifetime supply of Lucky Charms. I mean, and who doesn't want that? So you try to squeeze them, like I say, you can't do it. You try to bite them, you can't do it. Then you remember you've got a spacesuit on, so you wouldn't be able to do it anyway. But then you try all sorts of things. You can't figure it out how to tell, and so then you turn to your friends and wonder if they can help you figure it out. So what do you think? Ask yourself right now, if there's someone else with you, ask them, or talk about what you think you could do to figure out which one is filled with lead, which one's filled with styrofoam. Now remember, they're both in space floating around here. So it's not like one will feel heavier than the other, because the gravity is not affecting them, or it's affecting them equally or canceling out or something, so that they just seem to be floating there like that. So now we're going to try this. I happen to have 2 identical basketballs here, as you can see, perfectly identical. One of them is a heavy rock wrapped in a foam pad, wrapped in duct tape, and the other one is, looks like a playground ball. So we're going to first give them to Carly and Carson here, and just let them toss it back and forth and see if they can get an idea of what it would feel like in space even. Does it take much to get it started or to get it stopped?
No.
No? Okay, that's fairly easy. Now how about we take the one that has the rock in it and try that. You might need to get closer together. Oh, somebody always drops it. Somebody dropped it. Okay, that's good. Okay. So, if you were in space, though, remember this one would be floating around. So you wouldn't have to lift it up. And they kind of had to lift it up and throw it. But could you feel a difference in having to push it? Yeah. How about having to catch it? It definitely felt different, right? So that's the way it would be in space as well. I have another one here. But this one's on a cart, and it's a bigger ball. And I'll put the other one that was heavy on that. And now just give that a push back and forth a little bit. Okay, now let me take these off and see if you can tell the difference. Does it feel different? Yeah. There's less stuff to get going. Okay. So this would be the same in space. That with it being on the cart, then it's like you don't have to hold it up. So that's sort of like would be in space more. You just have to move it sideways. Or it's kind of like you're at the grocery store and your parents have loaded down the shopping cart and it's completely filled up. Fairly hard to get it started, and once it's moving, it's fairly hard to get it stopped. But when that cart is empty and light, doesn't have very much inertia, it's easy to start it and stop it. That same thing is going to happen in space. So we saw the tablecloth tug, that something in motion wants to stay in motion, or something at rest, sorry, wants to stay at rest. We saw the heavy ball, the two basketballs, lead and styrofoam. Now I want to show you the opposite of the tablecloth tug, that when something's in motion, it wants to stay in motion. And so my brother had a friend who went up to Alaska after high school, and he worked with a whitewater rafting company and helped guide people down the river. And on one afternoon, they thought it would be funny if they took their raft up onto a snowbank and slid it down in the snowbank right into the water. And we're going to watch a clip about that. Okay. So here they are up on the snowbank. There's 3 of them. And then they're going to slide down in the water. Something unexpected happens on the way down now. Watch that again. Okay. So you can see that when something's in motion, like the guy in the front of the raft, even though the raft stopped, he wanted to stay in motion. One more time, Carson, and then we'll pause it right when he hits the end. See it very well, but up in here, I can't quite reach it, but up behind the raft there, there's actually a rope tied onto the back of the raft, and either they did it on purpose or the rope just got caught in the rocks. And so when it hit the end, it stopped the raft, and the 2 guys in the raft in the back pretty much stopped, but the guy in the front went flying then. So things in motion want to stay in motion. All right, so I have here Thor's hammer. Don't ask me about how I got that. I'm not going to give away that secret. But I have this hammer, and Thor came to me and he said, I've got a bit of a problem. This hammer, the hammerhead's a little bit loose on it. I need you to see if you can fix it. You may be wondering why I can lift this, but that's another secret I'm not going to tell you. So the hammerhead was a little bit loose. And so the question then is, how do I get it to be tighter? And maybe you've seen people do this before with like a heavy hammer or an axe or a hatchet or like a splitting maul, is that you hit the handle on something and then it becomes tighter. So the question is, how do I need to hit it? If I hit the handle like this, is inertia going to make the head come off farther or go on farther? Or do I need to hit the handle like this? Well, let's try it. I've loosened this up a little bit more, or too much, so it kind of exaggerates it. So if I hit it down like this, you can see now there's nothing sticking out. So it actually went farther up, farther off the handle than it did before. Whereas if I hit the handle down like this, then it tightens it up more and shoves it more on the handle. So that's just a simple example of inertia that Thor can appreciate. All right, so here is our first experiment at camp, which I call the mystery mass. It's been around for a long time, but you take a hacksaw blade. Now you could use other things like a flexible ruler, but hacksaw blades actually have a lot of flexibility without busting, so they work well. And in camp we'll use like weights or something like weights or washers that I've weighed on my scale and know it's 10 grams or 9 grams or whatever the different washers are. But maybe you don't have a scale like this or a food scale to be able to figure it out. So what you can do is just use quarters. Each quarter is right about 5.5 grams. So I'm going to go 2 quarters at a time, and I'm going to tape 2 quarters onto the hacksaw blade on the end so they don't come off here, and then we're going to time it. Timer ready? Mm-hmm. 1. Let's see, on your mark, get set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It did 10 swings, and now Carson got the time, so he's going to write it down. While he's doing that, I'm going to put on 2 more quarters, which will bump us up to 11 grams total. And you'll want to make some sort of a chart like I did. You can just do it on a piece of paper or something. And now we're here. Are you ready?
Yes.
Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're timing how long it takes to do 10 swings. You can do less swings or more if you want. It's just up to you. I'll do 2 more quarters, and that brings us up to 16.5 grams. And I'm going to try to go all the way up to 100 grams if I can. Here we go. Ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you can see that it's taking longer. You can see it's moving more slowly each time. And that's what you want to see, is that it has inertia. The more mass we put on there, the more inertia it is, and the more it resists. And it's going to happen that same way in space as it would on the Earth. You could shake things to figure them out. So you're going to keep going all the way up to somewhere close to 100 grams. And then you're going to get some sort of a mystery mass object, or something around the house, maybe a bolt or something that you can tape on to the end. Something that you think is between 0 and 10 grams. I don't know if I have anything handy. We'll use this marker. It's not quite heavy enough, but that's the idea. And we tape like this onto the end here. And then Carson would time it. Ready, set, go. 2, 4, 5, 6, 7, 8, 9, 10. And then the idea is to try to use the data that you've got to predict how heavy this really is. How much mass does it have? What was the time on that?
2.7 seconds.
2.7 seconds. So you can make a prediction then based on the amount of time it took as to how many grams it is. What's really awesome is then if you have a scale, you can take the object that was your mystery mass and you can put it on a scale and you can see how close you were to the actual mass. One thing I will say, advice about the hacksaw blade mystery mass, is the timing is super important. If you get off on the timing or you round it up or down and just try to get close, it's going to throw off your answer. So be very careful with your timing. Redo a run a few times if you're not sure of it, and record it to at least 1 decimal place. So we've talked about inertia, and a hovercraft is a great explanation or example of inertia. Here's a homemade one I made around 10 years ago. This is a sheet of plywood cut into a large circle. Drilled a hole through this side and stuck a piece of pipe there. Got some Visqueen and made kind of a donut-shaped piece on the bottom, and then put a little plywood cap there and drilled it down. Cut 5 square holes here, and then just duct taped and stapled all this plastic down. So when we fill it with air, it'll inflate. On the bottom, lift you up off the ground a little bit, and create an almost friction-free kind of environment. Okay, so we'll have our first contestant here. Carly will sit on this cross-legged. I'll take a leaf blower that has a flexible hose here and put it down over the pipe. Get forward a little bit more. Okay, yeah. And then hold that. And get my cord all straightened out here. You ready, Carly? Yeah, here we go. Okay, now I'll have Carson come over and try it. Okay, he's going to get centered. Just scoot up a little bit more. Okay, go ahead and flip the switch. One of the tricks of a hovercraft like this is that you have to be centered. And if you're not centered quite right, Carson got off a little bit after I stopped him and he went kind of rolling, it doesn't quite go as smoothly. But you could see that once he was in motion, he wanted to stay in motion. And once I stopped the hovercraft, he kind of rolled that way a little bit. So that's inertia for you with a hovercraft. Okay, so we're here with our first build project at the camp. It's a hovercraft, which is really just a CD, bottle cap, and a balloon. And these have been made for a long time. It's nothing new here. They're all over the internet. But they're still kind of cool, and they illustrate the idea of inertia really well. So I'm going to start off by taking the bottle cap, and I need to drill a small hole in it. And I've got a block of wood here to kind of help me. And I'm going to take pliers here and actually hold that down so that I can drill without it going everywhere. You want to drill the hole right in the middle if you can. Okay, so we got a hole there in the middle. I want to peel off any kind of plastic that might be here on this so it's fairly smooth on that side. Then I'm going to take the bottle cap and glue that flat side onto the CD. It really doesn't matter which side of the CD you use. For people like the rainbow side kind of to be on the bottom. So you're going to put that there. The trickiest part is gluing it so that no glue goes through the center hole onto the bottom, because that'll act like a break. So you want to keep the glue away from the center hole, but yet still so that it'll touch the bottle cap. Kind of like that. I want to try to glue it so the hole is right in the center of the CD hole as well. It looks like I've got it pretty close there. So I'm going to set that there. Another thing I can do, you don't have to do this, but is to kind of make a collar to hold the balloon up. So take some cardstock or construction paper and lengthwise cut off a strip about like that. And I like to fold it into halves and then fold it again. I don't know if this makes a huge difference, but I think it helps to hold the balloon up a little bit. And then you can kind of put it around the balloon as a collar, sort of like that. I'll show you what I mean. Once you've blown it up about that big, you can twist it, and then it'll keep inflated while I put it down over the balloon. And you can see here that now when I untwist it, it hovers around like that, but the balloon kind of flops around a bit. So using the collar can help, and I'll show you what I want to do there. You can either take the balloon off, or you can just inflate it by using the bottom, whatever seems easiest to you. I've seen kids do it both ways. You can inflate it more than that, but the balloon tends to kind of flop even more if you inflate it more, so I'm not going to. I'll get the collar here. It's not cooperating very well at the moment. Actually, I did my collar too big. Let's try it a little shorter. I'm going to trim it down. That collar seems to be better there. It's a little bit harder to twist with the collar on there. But you can see the balloon stays up better and it hovers around pretty nicely when you do it like that.